Hello, my name is Aaryan Chatterjee, and this is my Lab 2 motion of a falling object in Physics 2211. Now, before we get directly into the lab, I think it's important that we understand what the lab is precisely covering, which is falling objects. In real life, objects falling straight down experience the forces of gravity and air resistance, which will affect their motion. Now, in this lab, we will focus on analyzing an object falling down and its motion and positions. More specifically, this lab will be focused on comparing an observational model, a computational model without air resistance, and a computational model that does consider air resistance to see how similarly or differently they describe an object falling down. Later in this presentation, you will see that both the computational model with air resistance and the observational model provide very close results, while the computational model without air resistance is not very similar, which can be seen on the graph on the right. Now, this lab is extremely important as it shows us how accurate certain models are, and it gives us an insight on how to analyze an object falling down. However, before we go over lab specifics, I think it's important to know the crucial physics principles that we utilize in this lab. Firstly, we use Newton's second law, which says net force equals mass times acceleration, or change in momentum over change in time. And this principle is important as it helps us make the velocity update formula, which will be how we define velocity in the computational model. Additionally, we also use the update formula to find the position in the computational model. Finally, it is important to note that the force of gravity on an object on Earth is negative mass times g, which is 9.8, and the drag force equals a drag force coefficient times speed of the object squared times v hat, which tells us the direction of the air resistance. Now, these forces will be needed in the computational models as they will affect the speed. Now, we must cover some of the major assumptions in the experiment, and one of them is that the object only experiences gravitational force and drag force, and that there are no other external forces acting on it. Additionally, we assume that the object only moves in the vertical direction, and more specifically in the negative y direction. On top of the assumptions, it is important to know that the system, which is what we will analyze, is simply the object used in the experiment, and everything else is the surroundings, like the ground and air. Additionally, the object's initial position will be at the origin and will be moving down, which will be the negative y direction in this case. We will analyze the ball for 0.633 seconds total, with the experiment starting at when t equals 0 seconds, and the object has an initial velocity of 0 meters per second because it's at rest. So for the actual experiment, I dropped a ping pong ball starting at rest and filmed it falling all the way to the ground, and this is my finished video. Additionally, in the video, you can see that the ball bounces off the ground, but for our current experiment, that part of the video will not apply since the scope of the video that we will be studying will be the moment I let go of the ball to the moment it hits the ground. So with the video, I inputted it into an app called Tracker and analyzed the ball's motion by seeing where the ball was at a different time intervals with respect to where the ball started. That gave me a chart of data relating to the object's position in the down negative direction, which I then inputted into Excel and made a graph out of, which we will see in the later slides. After the observation model, I then started to code the computational model that did not include the drag force. So for this model, I set the ball's mass to 0.0027 kg, which is the known mass of a ping pong ball, and I set the initial position velocity to 0. I then started my model at t equals 0 seconds, and I made the time increments of the model to be 0.033 seconds, since those were the time increments used in the observational model. Since we didn't include drag, I made the drag coefficient 0 and the drag force 0, which means the net force of the object was negative mg, which is the gravitational force. Then in the loop, I used the velocity update formula and the position update formula to update the velocity with the net force and update the position with the new velocity found. Then I ran my program, which is looped until the end of the experiment, which is t equals 0.633 seconds, and that gave me a table of position points, which I graphed in Excel with the observational model. So after making the first computational model, I then made another computational model that considered the drag force on the object. It was basically the same program as the first one, but it considered drag force now, so the drag coefficient had to be something. So in order to find the drag coefficient, which is 0.0023, I tested out different values and used a value that got to the closest position points as the observational model. Then in the loop, I calculated the drag force, which was the drag coefficient times the square of the object's speed, and it's important to note that the drag force will be in the opposite direction of the object's motion, so it will be in the positive direction, while the gravity will be in the negative direction. I then calculated the net force by adding the force of the gravity with drag force, and then I used this net force to update the velocity in the velocity update formula. I then found a new position using the position update formula, and then I finally ran the program and gave me a table of position points, which I graphed in Excel with the rest of them. So now that all three models are graphed, with the observational model being the points in blue, the computational model with no drag being the points in orange, and the computational model with drag being the points in green, I was properly able to compare all models. Looking at the graphic, it can be seen that the observed model and the model with drag are basically on top of each other, indicating that they're so similar and they had almost the same position points. Additionally, it can be concluded that the model without drag force starts off similar to the other models, but then starts saying the position is lower than the ball actually is, which means the model is not that good at properly predicting the real motion of a falling object. However, from this data, we can see that the computational model with drag is very accurate representation of the ball's position, indicating that it is a better model, which can further be seen in the next slide. These are the graphs of the drag model and the observation model, and since they're so similar, it further establishes the validity of the computational drag model. Additionally, it's important to note that the lab data could have been wrong due to tracker errors or drag coefficient being incorrectly estimated. Now, before I end this presentation, it's important to talk about some key questions. For the what does it mean question, the computational model that considers a drag force for predicted terminal velocity, we can see only model that has a force that can counteract the force of gravity. More specifically, eventually the drag force will equal the force of gravity, making the net force zero, indicating that there will be no acceleration, the object will have a terminal velocity. Now, it is also important to note that if the object had an initial downward velocity, it would still have the same terminal velocity, since the initial velocity does not change the fact that the forces of drag and gravity will eventually equal each other and make the object have terminal velocity. The initial velocity will simply make sure the object reaches terminal velocity quicker.